In this video, I will be going over electromagnetic waves in a vacuum using everything that we've built up in the previous videos from the paper. So something we didn't talk about in the last video is if A and B are both equal to 0, what that would mean physically. So something not covered in the last video, but we're going to cover is this. Consider A equal to B equal to 0, where again, your A is equal to F squared projected onto your scalar component, which is just equal to E squared minus B squared. And your B is just your projection onto F squared onto the quadravector component times the inverse pseudoscalar, which this is just equal to 2 times E dot B. So it's for these things being set equal to 0. So this means that if A equals B equals 0, then the magnitude of F squared is 0. But F itself is not 0. So it is nilpotent or null. So you see that when we're dealing with waves and we have some nilpotent bivectors, we're going to get into how our light-like behavior. So this implies that the global phase is degenerate. So you can have any phase, but it doesn't matter. That's not going to change the dynamics. So let's investigate a little bit more into that. We have first, we'll consider a field, and we'll derive that the field. We'll find out that if we're considering a field that has a certain property, that it is a nilpotent field, but we're not going to assume it's nilpotent. So first, let F be a field with a constant canonical bivector. And so what this means, if it's constant, is that you're having F defined as e to the phi, which could be a function of x, I, but here actually for now let's just have phi. And phi could be some function times f, and we're saying that it's constant, so such that the gradient of f is equal to 0. Well, this actually implies something, and I'll go through the proof after I show what it implies. This implies that the gradient of f simplifies to just the gradient of this scalar times this. So the gradient of the function phi times the canonical bivector, which is equal to 0. So let's have this proof. So for the proof, we're going to compute the foregradient. We're going to compute the foregradient of just f. So f is equal to the foregradient of e to the phi I f, which is equal to the gradient of phi times I times e to the phi I f plus e to the phi I gradient of f. Well, this second term is 0, so we end up with just the gradient of phi, and then I'm going to rearrange things. Gradient of phi times f times e to the phi I times I. Well, this function right here, or what I should say is rather, this I is just equal to e to the pi over 4, pi over, wait, hang on, sorry, not pi over 4, pi over 2 I is equal to, it's sine pi over 2 I, which is just equal to I. So that's why you have that whole thing is there is equal to that. So you can simplify the right-hand side. Phi f, and then e to the phi minus pi, or plus pi over 2 I. And we can just, from now on, call this term alpha. But we know that we know that if we take, so we say, let c here be equal to e to the negative alpha over 2 I. And for emphasis, this is a function of space. If we do that, then we can perform a phase rotation of this gradient of f here. But this phase rotation is just equal to, it's still equal to 0, but we can actually move this, have this commute with this vector, because this is a vector, so this will anti-commute with the, what do you call it? So these, let me see. So these anti-commute. So you end up with the gradient of, of f, because these c and f commute. So you can have c anti-commute here and then go all the way there. So you can have c star of x times c star of x. So you have these two right here, which this is just equal to gradient of f e to the alpha I. So it's the same, this is the same as this. But because, you can say because the gradient of f equals 0 and the gradient of f e to the alpha I equals 0, you have that gradient of f is equal to the gradient of f e to the alpha I. Then you have, because gradient of f is equal to to gradient of phi f e to the alpha I, right? You have this from up here, and you have gradient of f e to the alpha I, which is equal to gradient of f. We have that the gradient of f here, e to the alpha I, is equal to the gradient phi of f e to the alpha I. Therefore, we can cancel out the alpha i's here. So therefore, gradient of f is equal to just the gradient of phi of f, which is equal to 0. This is the end of the proof. So this is what we have so far. So, furthermore, if you have that the gradient of phi does not equal 0, and that f is not equal to 0, then you must have gradient of, you must have that f is proportional to the gradient of phi such that their factor, or their relative factor, is nilpotent. That is, these functions are equal to each other up to some constant, not necessarily scalar, but up to some constant, such that when you multiply these two together, those factors are nilpotent and thus null, and so they'll cancel out to 0 because of this right here. Well, because f is constant for all positions, x, that means that this change in phi must be 2. So it means that this must also be here, but this is, I'll say, like, this is logically equivalent to saying this. It's not talked about this in the paper, but it's logically equivalent to saying that the D'Alembert of f is equal to 0, which is, this is just a wave equation. So saying that this is constant in time is logically equivalent to saying that it satisfies a wave equation. So if this right here, oh, that was weird. If this right here is, or if this right here is constant in x, then the phi here must depend only on x linearly. So you can say, therefore, phi, which you can call it phi of x, is equal to some constant phi naught, plus or minus, the sign isn't super important, so plus or minus x, which is a 4 vector, so x dot the gradient of phi, where these are both, because phi is a pure scalar, like a real number, this is a real vector, this is also a real 4 vector, and this will be a real 4 vector. So I'll put that in here and emphasize this. So these are both 4 vectors. And so it's linear in time. And the reason there's a dot product is because there are 2 vectors here, and this needs to be this function needs to return a scalar, but it has a vector input, so you must dot product these together to get rid of any vector components so that these are pure scalars. And this implies that the gradient of phi has inverse units to x. So x has distance. So x has units of distance. So this right here has units of 1 over distance. What does this mean to have units of 1 over distance? This means that gamma phi, or sorry, not gamma phi, gradient of phi is a wave vector. Because in physics, vectors that are related to some phase and that have units of inverse distance must be wave vectors, because that's their role in physics. So this must be a wave vector. So you can rewrite as k, this, which is a relativistic wave vector, 4 vector. So you end up with this right here. And this changes the way the equations look. So you end up with the gradient of f is just equal to kf, which is equal to 0. Now remember how they must have a relative factor that's nilpotent, and this here is just a vector k. Well, then k must be nilpotent, and f must depend on k. Therefore, this k is nilpotent, and k, let's say it this way, k is an element of this bivector f, which means, such that f is equal to sk for some space like S and it's orthogonal, so S dot k is equal to 0. So this f is now a factor of, or is depends upon this k. Now, if we consider phi naught as being equal, so phi naught is right up here. If we have phi naught equal to 0, then phi naught equal to 0, then you have that f, which is the field again, and I'm just emphasizing again that it's a function of x is equal to sk, which comes from this right here, times e to the plus or minus x dot k I. And this is a plane wave solution. So right here, we have found an equation for a wave, for light. So this right here describes how light works. But let's rearrange some things so that we can see how this relates more easily to traditional wave mechanics. So a space-time split of k gives k is equal to gamma naught, one, or not 1, omega over c minus k vector, where omega over c is frame dependent is frame dependent frequency, and k is frame dependent, or is the frame dependent wave vector. Furthermore, if we consider the square of k, which we know is equal to 0, well, we know that this is same as performing, or if I go up into the space-time split, the definition of a space-time split, you can also have gamma, which will commute with this, so you can have omega over c plus k vector and then gamma naught. So these two things are equivalent. So when we square it, we can just use both. So when we square this, we can have omega over c plus k vector, and you have gamma squared. Then you have omega over c minus k vector squared. And this just is omega squared over c squared minus k vector, the magnitude of k vector squared. Which implies that omega over c is equal to the magnitude of k, which this is a known result. It's called in electrodynamics, this is called the dispersion relationship, and this holds in any reference frame. So basically, this is the same thing as saying that all reference frames see light the same. This is why. This is what's happening. When every reference frame sees the same thing, then it's a nilpotent. It squares to 0. We can also rewrite k as being equal to, we can pull out this factor here and call this k naught, which would be the same as having a 1 minus or 1 plus a kappa, 1 plus kappa unit vector, gamma naught. So where this kappa is just the propagation direction. So this kappa is just the propagation direction of the wave. And an important thing to note is that this k naught, which is equal to this here, is unitless. It doesn't have any dimensionality. So all the dimensionality is encoded here and none of it in here. So this implies that kappa times f, this little bivector here, is just equal to f. And so I'll do a proof. So proof first you have kappa vector, which is equal to f, or times f, which is equal to kappa vector. I've never written my kappa as well. It's just how it is. Equal to sk, which is equal to negative kappa k s, because of this ks here, they anti-commute, and where that was found was here because their dot product is equal to 0. So sk is equal to negative ks. So then you can break this out into its space-time split. So k be 1 plus k gamma naught s, which is just equal to, expanding this through, negative, and then you end up with kappa plus, then kappa squared is just 1, then gamma naught s, which is just equal to negative ks, which is equal to ks, which is equal to f again. So come up here, steal this. So you have that the canonical bivector is an eigenbivector of this propagation direction, which is a relative frame. So that means that this canonical bivector, when broken into the correct frame, is broken into the correct frame, state remains the same. So this could be thought of as a way to, or this kappa is contained, like if this kappa comes from a particular reference frame, then f will only be an eigenbivector if the, what do you call it, the relative, the space-time split of f goes into the same reference frame as this kappa. So okay, we have that. But another thing that this implies that kappa, if kappa times f, so if we break down f into its space-time split here, is equal to kappa E plus kappa BI. Well, we know that this is the propagation direction, and when you're in a relative frame, the propagation direction is perpendicular to the electric and magnetic fields. So we know that these right here are equal to the cross products. So you can say that kappa cross E, you're going to have this factor here just because of the definition. So you have kappa, because if you have, what do you call it, a bivector times another bivector, then you're going to have the scalar component. So scalar component, you're going to have, and then you're going to have the bivector component, and then plus this right here. Well, the traditional notation in this framework would be to say this, which this is equal to kappa cross E I, this right here. So we can use this relation. Oh. Then plus, and this would actually be a minus because you end up with something similar here, kappa cross B, because if you have a plus here, you have I squared. That's just -1, so you end up with a negative sign here. But because this is an eigenbivector, so we know that we end up with E plus BI again. So we have this. This implies, so these two things imply that kappa cross E is equal to B, kappa cross B, or kappa, or I'll do this instead, B cross kappa, I'm just flipping because there's a negative sign here, is equal to E. And we know that kappa here is in the propagation direction, which is perpendicular to E and B. So we know that if we took E and then the unit, so the magnitude, so E, so 1 over E, and then E cross 1 over B, this would just give kappa. So all three of these vectors are mutually perpendicular. And if they're all mutually perpendicular, then that implies that kappa times E, where I'm just going to use the hat again, times B, use the hat. This is just going to give the pseudoscalar. So this means that when you go into any relative frame, you use a space-time split to go from a space-time algebra to a relative frame, then you're going to have a right-handed set always. You're always going to have these three things be perpendicular. So that's what the pseudoscalar is representing. It's representing this breakdown here. So it's a right-handed basis in any relative frame. So another interesting property of this, so therefore, because of kappa E equals B, or rather equals BI, because kappa E equals BI, you can pull the E out of this, pull E out and have or E minus kappa. You should have E minus kappa, and this will be your canonical bivector, which further implies that your field is equal to E1 minus kappa E plus or minus x dot k I, which we can further simplify and make it into more of a traditional form. You have E1 minus kappa, then E to the plus or minus omega t minus the relative position in a space-time split, and then the 3k vector, wave vector I. So this is how electromagnetic waves come out of the space-time algebra. And a really cool thing about this is that when electromagnetism was originally studied, they wrote waves with complex numbers, not for any reason, but just because they simplified them. It simplified the math. They didn't have to write cosine and sine every time they wanted to do something. That was the only reason that the Euler's number was used for a wave when it was first introduced into physics. But then they found out that the eye actually produced meaningful physical results, and so it's been a part of it ever since. But in the space-time algebra, it was never introduced as a fundamental part. It was derived from the geometry of the algebra itself. And so the geometry of the algebra gives rise to this. So it tells us that the putting e to the I, or having that complex number representing a wave, is not ad hoc. It is a fundamental part of the reality that this describes. So that's something that is very cool about this approach. But here, let's go back up. So I already showed this section, but then let's look at this. And like that.